Today we're going to look at the mock final for MATA30, and we're going to go through the solutions. Okay. Recall that these solutions are not meant to be 100% solutions, but help you understand the process behind these questions, help you get 70, 80, 90%. I will also be talking about the theory behind these solutions that will help you understand what's being asked and what other questions could potentially be asked about this theory. We start with our part A questions. Here we've got compute the derivative of arc sine of x squared. Now here, this is a chain rule. We need to know what the derivative of arc sine is, and we need to know what the derivative of x squared is. So the derivative of arc sine is 1 over the derivative with respect to x of arc sine of x is 1 over root 1 minus x squared. Because it's x squared, the derivative of arc sine of x squared, this derivative is going to be 1 over root 1 minus x squared times 2x, or 2x over the square root of 1 minus x to the 4. That is our root. Okay. Now, question A2. Let v of t equal 3t be the velocity of the car. What is the function's position? What is the function for the position of the car, s of t, if s of 0 equals t? Now here we've got position, velocity, and acceleration. If I derive that gets me from position to velocity and velocity to acceleration. To go from velocity to position, I integrate with respect to t. To go from acceleration to velocity, I integrate with respect to t. Now, when I integrate with respect to t, I'm going to have a constant of some kind. I don't know what that constant is, and I need an initial condition to solve for that constant. So s of t equals the integral of v of t with respect to t. So s of t equals the integral of 3t squared dt, which equals t cubed plus c. Now we're given the condition that s of 0 equals 0 cubed plus c, which equals 10 from our initial condition, which means c equals 10, so s of t equals t cubed plus 10. So s of t equals t cubed plus 10. Here we have compute e to the x, secant squared e to the x. This is a u substitution. U equals e to the x, du by dx equals e to the x. 1 over e to the x du by dx equals 1. This equals the integral of e to the x over e to the x secant squared e to the x du by dx dx, which equals the integral of secant squared u du by dx dx. That equals tan of u plus c. And with u being e to the x, it's tan of e to the x plus c. Okay. Now here, there was a typo here. We'll make this 5x. So here, with it being plus 5x, the derivative with respect to x of f inverse of 20 is going to equal 1 over the derivative f inverse of 20. So there's two things I need to know here. What is the derivative of f of x? And what is f inverse of 20? The derivative f of x is 1 over x minus 3 plus 5, whereas the derivative of f, or the inverse of 20, is what plugged into this expression gives me 20. And if we look at ln of 4 minus 3 plus 5 times 4, this equals ln of 1 plus 20, which equals 0 plus 20, which equals 20. So x equals 4. That's f inverse. So f inverse of 20 equals 4. So now I'm looking at 1 over 4 minus 3 plus 5. F prime of 4 equals, which equals 1 over 1 plus 5, which equals 6. So this equals 1 over 6, 1/6. Okay. You could also have altered it to be ln of x minus 4 plus 4x. And if you did that, my answer would be 1 over 5. Here, this is an interesting question. It says set up but do not solve the improper integral. What we mean by set up but do not solve, we have to figure out why this is an improper integral. And an improper integral is given from a domain constraint. So I'm going to look up determine the natural domain of this function. And to do this, I need to factor. So minus x squared plus 8x minus 12. I'm going to do minus 1 x squared minus 8x plus 12. There, I'm going to multiply to 12, add to 16. That is x squared minus 2x minus 6x plus 12, giving me x minus 2, x minus 6. Okay, with a minus 1 out front. Now, this is going to be a parabola that looks like this at 2 and 6. Well, my integral is from 2 to 5. So I'm going to take 5 and I'm going to go up to a point BA, which is slightly greater than 2. I'm going to integrate over that bound and then I'm going to let A approach 2. Or I'm going to take the limit as A approaches 2 from the positive of the integral A to 5 of 1 over root minus x squared plus 8x minus 12 dx. The 5 is just fine. We don't need to change the bound for 5, but we do need to change the bound for 2 because I can't divide by 0, and this square root will be 0 when x equals 2. A6 is a question similar to something we've done multiple times. We create a function that is not a piecewise function with a natural domain. When doing this, what we want is we want a domain that goes from minus 2 to 4 and then 6 to infinity. And the way that we're going to do this is we're going to combine some functions together. The first thing that I'm going to do is I'm going to break this up into minus 2 to infinity. And then I'm going to make another function that goes minus infinity to 4 up to 6 that goes on to infinity. So here, this greater than minus 2, this function here, I can make that using ln of x plus 2. That function there will now be positive whenever x is greater than minus 2. Now here I have this jump from 4 to 6. To deal with that, I'm going to do ln x minus 4, x minus 6. And the reason why I'm doing that is because that quadratic, x minus 4, x minus 6, is a positive quadratic with roots of 6 and 4. And the ln function is only defined when I'm strictly positive, so I'm not defined here, including the 6 and 4. Now, if I combine these two functions or add them together, the natural domain has to satisfy both this and this. So it's the intersection of these two domains, which is the original domain we wanted. So I'm going to use the function ln of x plus 2 plus ln of x minus 4 times x minus 6. Okay. Now we have the first derivative test. We need to define the first derivative test. The first derivative test says let C be a critical point. If f of x is increasing, or if f prime of x is greater than 0 just before C and f prime of x is less than 0 just after C, then there is a local maximum at C. If f prime of x is less than 0 just before C and f prime of x is greater than 0 just after C, then there is a local minimum at C. That's the first derivative test. Remember, our derivative tests classify our critical points. So the second derivative test enables us to classify our critical point, and the first derivative test also classifies the critical point. They don't tell you anything about concavity or increasing and decreasing. No, they are tests that classify the critical points. Now, to compute this antiderivative, computing the antiderivative, I find it easier to compute the indefinite integral and then just pick one of them because it's an antiderivative. Here, this is a U-substitution. I'll leave it as an exercise for you to show that this is e to the x squared plus c. And because I'm picking an antiderivative, I want to fix this c. I want to pick a constant. And because I am like to be a little silly and I can pick any constant, I'm going to pick plus pi to the e. Okay. A9, we're given the velocity of a car. What is the acceleration? Well, v of t equals 3t squared. Remember our discussion earlier where we said velocity, to go from velocity to acceleration, we take the derivative with respect to time. So our a of t equals 6t. And it's saying, what is the acceleration at 4 seconds? So a of 4 equals 6 times 4, which is 24. So it's 24 meters squared per second. Or sorry, meters per second squared. Finally, we're asked to draw a graph of a function with domain -2 to 5 function must have a local maximum at 3 and a global maximum at 5. The function has no global or local maximums, but has an infimum of -2. So here, I'm going to draw a graph. Here, I'm going to label -2, I'm going to label 3, I'm going to label 5, and I'm going to label here -2. And I'm going to draw in a local maximum that looks kind of like this, and a global maximum here. Okay? Now, I'm really tempted to do something like this, where I put a little circle there to give myself an infimum. And then I come down and really tempted to have this arc. So I have my local max, check. I have my global max, check. I have my infimum at -2. But here's my issue. This is a local min, and it's told I have no global or local minimum. So I need to somehow get rid of this. And it turns out we can't get rid of this using a continuous function. Actually have to have some sort of jump discontinuity, or we could also do a removable discontinuity. Both could come down to here, and I have a single dot that jumps up here.